Last week, Elon Musk announced some massive numbers of Tesla bots he's planning to build. Next year, 50 to 100,000 bots. But did you realize that actually Elon purposely delayed the final design lock of Optimus, waiting until version 3, that he said will have hands that have 22 degrees of freedom and the actuator moved from the palm to the wrist and using tendons instead. So why was this so important that it was worth a significant delay? We have Scott Walter, a two-time robotics company founder, with us today to give a deep dive explanation of what Optimus is now able to achieve, how much larger the market becomes, and why it was important they did this. The hands of TeslaBot will allow it to handily win over its competitors. Welcome, Scott. Thank you for joining me again.
Hi, Herbert. Welcome to 2025.
2025, you took a break, but this video of Optimus being able to catch a ball, that's something wanted to talk to you about, because this is it, right? We finally have the announcement that he made, 22 degrees freedom, but more importantly, it's integrated right into the wrist. Why don't you go ahead and share a little bit of why they did this?
Yeah, and even more importantly, it's integrated into the Gen 2 bot, but we'll get to that in a little bit. But yeah, if you play the video, of course, you can see that there are two different hands on here, and that the Optimus is able to catch a ball. And we can see that it's not a fluke because it happens like 2 times in a row going on there. And of course, there was a lot of excitement about, oh, my goodness, so Optimus can go ahead and do that and catch a ball, and it's more than just about the hand. Now, Elon was very quick to make sure everyone knew that this was not autonomous, that this was teleoperated. And that kind of caused like a little bit of disappointment from everyone. It's like, oh man, it's like, it's not it's not autonomous, it was teleoperated. But there was a lot more that Elon sort of had in that post. So, the first thing he talked about that and some of the other details they'll be able to get in through. But the main thing is, it's like, I didn't care that it wasn't autonomous. In fact, that wouldn't have impressed me that much. I'm actually way more impressed about the teleoperated control. And we'll kind of get into the details and the reason why that, as well as the hand. So the main reason why I'm not that impressed about the fact that it wasn't autonomous is because that's already been solved. That's already a problem. And I've got a video coming up here that's it's like over 10 years old from Kuka Robotics that's showing like an example of being able to have a robot track a ball in real time and interface with the thing. And so this is a long time ago, way before we had like advanced AI, using basically old school methods of having a camera tracking. And the whole point of this thing was not so much that it was a ping pong playing ball or table tennis playing ball robot, but that the robot had the agility to be able to move around that quickly. It had the velocities, it had the accelerations. They really definitely were showing off the mechanics more than the software here. So it's very impressive when you see what's going on, and you can see there was like millions of views. It was a very interesting thing. So that's kind of a solved problem. The real thing is that when you come into being able to do the telerobotic control on there, tells us a lot about the reaction time that the bot has to have. So if you think about what's going on, in order for me to catch a ball, I have to both see it and then be able to react to it, and then see that my reaction time is following along with it. So
I'm just playing this.
Yeah. So again, we kind of see there that the bot's able to move around at what seems like superhuman speeds to be able to track the ball very quickly. Okay, so it's really not a big deal to be able to track something like that. Even if it's not grasping it, it's at least being able to track it in the air. Not a big deal. Of course, being able to do the grasping with any sort of robotic hand is a bit tricky. And if you're doing it telerobotically, you need to get rid of the latency. So that is something that actually impressed a lot of people, that, they've said, wait a minute, telerobotically control that. Think about what's going on. You're putting on a VR headset. You're looking at it from the point of view of the robot. That point of view may be distorted a little bit because, remember, it's got kind of a fisheye. So it might be kind of a strange environment you're in. And you're trying to track a ball and move it around and hope the bot reacts as you are reacting. Because, if there's a little bit of lag going on there, that's going to be very hard to be able to intercept the movement of where it's going on there. Now, the other thing is, you've got to remember they're doing a few things. So if we kind of go back to the picture that's there and show how they're doing it as we run this, we can see, let's say, what the trick was doing. And a lot of times the trick to the catch is all in the toss. Okay. It is, if you want somebody to catch something, you make sure you throw it to them so they can catch it. This is something that NFL quarterbacks do every Sunday. Okay.
Yeah.
They are trying to throw the ball to to make sure a certain person is able to catch the ball, another person not. And so the way it's being done here is first is you don't throw a fastball, you toss it. So you can see it's a very simple toss. The toss is towards the face, which is basically where you want it to be, because it's going to be very hard if it's down low. Because again, you're
I
trying to
see.
see it through there to make sure it's there. But at the same time, you've got to come through and you've got to be able to react and be able to get it. And the two things that are going on here in the telerobotic control, one is you need something to be able to move the arm to get there. The other, you got to make sure something is able to close the finger. So I'm it's going to be curious to see what kind of controls they're using for the hand. Does the hand just close right now, or do they have individual movement on the fingers? Do they have some sort of data glove that's being able to do it? So so that makes it a little bit easier. It was a consistent toss in the same place every time. He's anticipating where it is, the same way that a baseball player, a batter is like anticipating where the ball is, because you can see the wind up and figure out everything that's going on there. There's a little bit of that going on there, but still at the same time, it's very impressive to be able to get that and get the reaction to be able to do it very quickly. And we were able to see some other things about the overall movement of the arm. So you notice it wasn't just the arms moving, the torso was a part of it. So the torso had to be able to come around to be able to get that. I'm wondering how they're doing the tracking on that, and whether
Yeah.
the telerobotic kit has tracking on the torso, or whether that's more of a full body control that they kind of realize, oh, it would actually be a good idea to move that. Now, of course, the legs have to, or I should say the pelvic area has to adapt to that, because there's some movement down there, but that's movement is a consequence of the upper body. It's not because the operator is moving his legs or something like that. It's what the robot's going to do to maintain its balance. As you run this, you're going to notice that the feet shimmy a little bit at the end of one of these moves. And you would expect that as you start to move the hand, you're going to get that reaction force on the floor, and that the feet should actually go in the opposite direction of the way he's turning. But you'll notice it actually goes the other way. So what ends up happening is that as soon as he catches the ball, he basically is trying to stop the movement of the bot, and the feet just suddenly slide on the ground. So I thought the friction on the ground would be enough to not have that, but there's a little bit of movement, which tells you a little bit about how rapidly the bot's able to respond to something like that. So it's like its deceleration was suddenly high enough that it caused a little bit of slippage on the floor there. That's rather interesting as far as the capabilities of what you're seeing in the arm. So in order to move quickly like that, you need to have a really good telerobotic system that has very little latency. So the data is going from the bot to the teleoperator, from the teleoperator back to the bot. But the most important thing, you need to have a bot that's able to respond to those commands very quickly. And we all know what that's like driving an ICE vehicle versus an EV. An ICE vehicle, you put your foot on the accelerator and nothing happens. And then finally it gets going, okay? But we know that when you have an EV, you touch that thing and it does exactly what you want it to do instantaneously. So you have way more control, much better. So it's the same thing is going on here, is that when he says the hand has to be here, the hand is there. And now usually it works because there's physics happening on both sides here. There's like both the operator is limited and how quickly he can move his hand from here to there, and the bot as well. But if you had something that there was like the two of them were somehow out of sync, or there was a glitch that suddenly, let's say the robot's hand is over here somewhere, and mine is there, and I want it to go to here. Well, I have a small movement, and suddenly the bot wakes up and realizes, oh, you want to be over there, and it's like it just can't get there very quickly. But for the most part, because they're synchronized together, the movements are small. So my rapid accelerations, it's able to respond to that also as well. And that's very important to have enough. So you don't have infinite acceleration. You don't have infinite velocity, but you do have a fairly good enough amount of it that you can do that. If this is a virtual robot rather than a real one, you can turn up the acceleration to anything you want. You instantaneously can jump from one space to another very, very, very quickly. But in the real world, you can't. So that's why it's also very impressive. And I've done this kind of things before, but with virtual bots, right? I don't have to worry about the speeds and accelerations. I've got as much as I need on tap. In the real world, it's a little bit different. Plus the fact there's differences between the kinematics of the operator and the bot. The bot's going to make sure it doesn't fall over, because there may be some position that the operator can get into where he's perfectly in balance. But if the bot attempts to do it, because its center of gravity is a little bit different, will just kind of fall over. So there's a lot of times the movements you're doing almost have to be a recommendation of what you would like it to do, and not a literal, you have to exactly go there. Try to take my intent and get there. So going through and getting the ball is something else. Now, the other thing that Milan talked about in there is grasping the ball was difficult to do with the first generation hand. And it kind of surprised me to say that, they actually couldn't grab it, or maybe they get very lucky every now and then, but most time it was very, very hard. And what would be the potential reasons for that? So if we can look at a couple of slides here to remind everyone,
Yeah.
what's the
Let me
difference between
show.
the hands?
Right. So this is actually the original hand that they were
Yes.
showing, just so folks can see it. And at that time, it can already grab, pick and place
Hmm. Hmm.
different blocks. And remember how one of the blocks even fell, and he was able to
Right.
reset
Right.
it up.
But
Okay, so that's
but the blocks are static. It's kind of
mhm,
slow and everything else to be able to do it. So you have plenty of time to grab something. Whereas when something is moving through the air, you've got to track the thing, you've got to react to it, and then you've got like one chance to grab it, and it's got to happen really, really quick.
mm,
Um, and again, we can see the telerobotic control. It kind of looks like the robots are wearing gloves, because the hands are kind of splayed out. So it looks like they have about as much dexterity as a person would have wearing some thick winter gloves. Um, and so that's the level of dexterity. Whereas what you have now, so if you go back to, I think a couple of the slides I have there, we can start to do it like a side by side comparison. So the first thing, when you look at that hand, if we did not see that on Optimus, if we had just we're just focusing on the hand, you would swear that's a real human hand.
this one here,
I mean,
you bet.
everything about it, yes,
Hmm.
everything about it's like, my goodness, is like the
Hmm.
proportions of that, everything, it's the same. You've got different
Hmm.
finger lengths. You can see where all the knuckles are, and it just looks like, someone is wearing a latex glove, and that's
Hmm.
absolutely it. And that's like the first thing I found is remarkable. The second thing is like, interesting. They chose the left hand first rather than the right hand.
Well, why?
Uh,
Hmm.
Good question. Why they did that, I don't know. Whether maybe this particular operator, who is like their star
Mm.
operator, is left-handed. I don't know.
Hmm. Hmm.
And the other thing is like the integration with the Gen 2 bot seemed to have been like really easy. So I thought for sure that because there was so much changes going on there, it wouldn't be as easy as like taking one off and putting it on there. So it's like, oh my goodness, it's very clear that they removed the other arm they have on there. But we can start to do a comparison between the two to see the major differences between the old 11 DOF. And
Yeah.
one of the first things that jumped out to me are the cables are gone on the other side. I mean, you can
Hmm.
see all the cabling that's there, but if you look at the new hands, like, man, even the elbow cables we can't see. It'd
Hmm.
be one thing to say the stuff around the wrist, they managed to get rid of that, but you're not even seeing around the elbow. And that's rather remarkable that they're able to do it. And then we can kind of get a side by side. I think I have a slide up here that gives us a pretty good idea of what's going on there. So the first thing is that the old one has the Popeye forearms of those two black linear actuators
Yeah.
that are used for just the wrist movement, just the wrist
So,
movement.
yeah, I was going to ask you that because the whole point of what he said was the old hand had the
Mm-hmm.
actuator in the palm and they wanted to move it to the wrist. So if
Yeah.
they did that, theoretically, the wrist should actually get thicker, but in fact, it
Yeah.
got
Yeah.
thinner.
Yeah.
So
You'd think,
what did they
wouldn't you?
invent? Yeah,
Yes.
what did they
I mean,
invent here?
that was the very first thing I thought. I was like,
Yeah.
well, it's already crowded down there in that forearm. They're going to have to make room. So they might be thinking of a different strategy for being able to do it. So we can look at that hand, and there's a lot of subtle things about it. Is that the number of finger joints they have is less than in an actual human hand. So they have basically one IP joint, what's called an interdistal phalange kind of joint, what they call it either a dip or a pip joint. They have only one, where you would normally
One.
think of that you get your two knuckles there.
Hmm.
So they reduced that because they wanted to simplify the problem. And now they have all of the IP joints that you would typically have in your fingers. So that's
Hmm.
the first thing. The other thing is they added the degree of freedom to allow the fingers to splay out. Now, why would that be important when it comes to grabbing a ball? Well, if I have fingers that can only do this and can't do that, when I go to grab a ball,
Hmm.
it's like they're coming down kind of like that. I mean, it'd be okay for grabbing maybe a bottle or a pipe, but for something spherical, I want my fingers to be able to come out. And that usually means spreading them. So a lot of things that you want to grab, it's a lot better to have what they call the abduction movement that's kind of going on in there. And so that means their fingers at that joint, which is the MCJ joint, has now 2 degrees of freedom, whereas the old 11 degree of freedom one had it. The other thing is that was 11 degrees of freedom, but there were
Hmm.
6 actuators in there, and they were all in the palm. So they had to shove these actuators in there, and it was tendon driven. So even though the actuators are in the palm, it's not a mechanical linkage that's going between them, but there actually is a tendon drive that's going on in there. And I think I've got some images coming on up of reminding us of what the old one. Okay, again, we can see all the cabling that was in the
Cables.
old one, kind of what
Right.
it's looking like. And then I think go one or two slides down, maybe a little bit further, we can remind ourselves this is what the original design looked like, where you might be able to sort of see where they're thinking of putting the motors in there. There's another image in there to give you an idea of the kind of tendon drives that they have that were going up. So there were tendons that were going down there. And the next image up, we'll see what the actual actuator looked like. So you'll see they have this actuator that's got that long gray motor that's there. And then you have a rack and pinion kind of design there where you've got a worm gear drive that's spinning around that's causing the blue gear to rotate. And on that blue gear, there's a little bit of a space there that you tie the tendon on and allows it to wrap around it like a spool. So that's how they were making the tendon go up and down. If you think
right
about
there.
it, that takes up
Gotcha.
a lot of room. And of course it's very close to where it needs to be. So it was like actually very close to where they need to do it. And we don't know what those tendons were made out of. They may have been made out of like some sort of synthetic fiber, like an aramid, which is similar to like Kevlar or something like that doesn't stretch, or they may have made it out of something metallic. It's like a piano wire string or something like that. And the thing about that is that means you're winding it around, and whenever you're winding around the spool, you're going to be causing fatigue, and it also takes energy to constantly, because you're bending this metal back and forth and back and forth. So a lot of times you don't want to do that, and that's why a lot of people have kind of given up on tendons because they're finicky and trying to find out actuation strategies doing something like that. So now imagine taking that big bulky motor and then trying to move them into that forearm area. How do they make it on down there and get the actuation strategy? And the other thing is that as we begin to look at it, as we talked about, they have like a tendon in each finger. Tendons have a problem is that they only work in one direction. They work great in tension, but they are really bad in compression. So you can use them to close your hand, but the only way you can get them to open is that you can relax it, but the fingers won't naturally go. You can try pushing them, but you won't really have enough force to open it. So in some of the images, I think if we back up on one of the images where he's grabbing the egg, you'll look really closely and you'll see at each joint, right there, if you look kind of closely, it's like, especially the index finger that's touching the egg up there, you can sort of see a spring mechanism in there. That's a torsion spring that allows that joint to pop open. So when you relax the tension on the tendon, it will pop open. So that means you've got a lot of strength and energy in the closing or the flexion of the hand, but you've got very little in the extension. It just opens up based on whatever that spring constant is. And so that's one thing that they're kind of lacking. You have one tendon that allows you to close it, but there's nothing you can do to open up. And that's why there's a lot of other designs like what Figure has, I think the Xipeng Bot and some others where they have more of a mechanical linkage so that what they're actually connected to, you just run the motor backwards and the finger opens up. Now there's another challenge to having is that everyone will talk about 11 degrees of freedom. So they're talking about like the number of joints that can move around, but some of the joints are dependent. So in the Optimus Bot, you had like 2 degrees of freedom on the finger, but it was connected to one actuator. And they were not independent, which meant when you pulled on that actuator, both joints started to bend and you could not control one over the other. And now that you're going to the 22 DOF, you've added one more in there, which means they're all kind of coming on down there. And the problem that the original Optimus had, because of that strategy, when it went to close its finger, it had this clawing action where the hand would just kind of close on down. Exactly. Yeah. And so the problem with that is that if you just kind of zoom in for a second so we can kind of see is that when you have a clawing strategy, like, normally I want to grab something like this. I want my finger to come and be able to close around it. But if I have a clawing strategy and it closes like that, I can completely miss my target. So what I want to be able to do is have my fingers start out straight at first and then allow them to come around. And I don't have that control that way. The only way I can keep the other joint from moving is if it comes into resistance, because, then it's pushing against the spring and the tendon and everything else. So you don't have that kind of control to be able to do it. So what are they doing in the 22 degree freedom hand? And we'll begin to see what's going on there. They seem to have a ton of tendons on down there.
Crazy.
And I've done a breakdown of what's going on. And it turns out they don't have one tendon in the finger. So it turns out in our actual hands, we have 2 tendons, which act as the flexors, 2 flexor tendons. And we have one that's called an extensor. So in the human body, there's actually 3 tendons that are controlling the opening and closing of your fingers. The reason why we have 2 here is because our grasp is way more important than the extension that we want to get there to be able to get the strength. They decided to say, we're not going to put those springs back in the knuckles anymore, because now we're going to be putting extra springs in there it's going to be much more difficult to kind of pop it open. They actually have a tendon dedicated to opening it up. And we'll jump on down here, and I've got some images sort of showing that aren't just videos, but labeling what's going on in the hand. These are all the joints. This is where the 22 degrees of freedom come from, okay?
Yeah.
So you've got those dip and pip joints, which are basically what we all call the knuckles. And that calls, it's the distal interphalangeal and the proximal interphalangeal. That's why they call them the IP joints. And the MC joint is basically where the finger attaches to the palm, okay? And you have 2 degrees of freedom at the MCJ and only 1 at each of the IP joints, okay? So that means each finger has a total of 4 degrees of freedom that you have there. And if we look in really closely, we may begin to notice where the tendons are. So if go to the next slide, and we'll see, okay, you'll see there's a tendon right down the middle. That's the flexion right in there, right, that I've got circled in red there. That is showing you the tendon that is allowing the finger to close. And then we have the movement back and forth, which gives us, the famous live long and prosper, the ab and adduction. And that's actually done with 2 different tendons, because what happens is that you pull on one tendon, it's that way. If you relax the tendon, the finger's still going to stick there unless you have a spring to make it go back. So that means, like puppet strings, they need to have it on both sides in order to go ab and add. Okay. And now we'll go to the next picture, because we can't see it in here. Whoop, on the top, when the hand was closed, we could say, wait a minute, there's some tendons on the top. So those are the extensions that allow them to be able to open it back up. That means every single finger has 4 tendons. And by definition, a tendon has one end that's like attached to bone and the other end that's attached to a muscle. Okay. So that means the other end, the muscle in this case, is the actuator. So we can see all those tendons down the bottom there that are being routed through the actually the carpal tunnel, and they end up attached to these different actuators. Now, notice the different actuation scheme that's on here. So I think if we go back up to one of those videos, I'm not sure if that one is there, one of them by 30 Tesla, and we can start to look at what's going on.
I don't have the videos.
Oh, I think is a video in there on that, on the movement?
No, I have my own videos that I got, but I mean, was it displayed here where it was like this thing? That's what you're referring to?
Yes, exactly. So we can go ahead and see that. And if you look really closely, you will see how the tendons are being pulled up and down, up and down, up and down. So the actuators are a linear actuator. They're not this, what's in the current Tesla bot, where they actually have it on a spool. That's overly complex, because you need to have that worm drive, or basically that rack and pinion, and the thing to kind of spin it around. It's really bad for tendons doing that. This way, the tension is always like in a linear direction. It's in the same place, and it's way more compact. So that's one trick that they did to be able to take, those very what I would say were like overly designed, much bigger actuators that are in their palm, and then move them down there. So that's a very important thing that they did, of coming up with a simpler design, of figuring out how to get the range of motion that they needed to be able to do it. And that might be part of the trick, because everyone that's dabbled with using tendons will tell you that they're finicky, they're difficult. The maintenance on them is a problem. They break, they stretch, getting them calibrated in there. And some of it can be like, if you're winding it around a spool, yeah, that's just going to cause a problem. You've got other issues that you've got to kind of deal with. But if you're just kind of pulling them up and down, that can simplify a lot of the problems. There's not just a space claim issue that they've been able to fix there, but it can also cause a lot of the issues of the overall reliability of the system. So that's one thing. Now, they've gone from 6 actuators in the 11 DOF to somehow 24 in the 22. And you're going to say, well, wait a minute, how do you get to 24 if there was 22? And a lot of it, again, goes down to some of these weird degrees of freedom that they have, that basically every single joint you have there, you almost need to be able to have, well, in some cases, they're dependent joints, and other ones that they're independent. The thumb has 5 degrees of freedom. So if you look at each finger, there's 4, right? There's 4 actuators needed for those things, because of the 4 tendons that are going through there. So that gives you 16. You go to the thumb. Well, the thumb is actually 5, and you need 1 for each direction. So that, again, is going to pop you up that you now have the extra. Okay. So you get you actually end up getting 6 there that will get you up to, another 4, right? That gets you to 20 plus another 2, the 22, and then you have that palm. So you see the red one there, that's for the palm. That's right underneath the pinky. Whatever that one is there adds yet another, it's another degree of freedom, but it requires 2 more servos to be able to do it.
Yeah, that's
So
great
that's how
that
you
they
get,
did that, by the way, because
yeah.
that
So
means you can bring down that side of the. Sorry if I can do this
yes,
properly, but
yes,
that is
yes.
great right here.
Yeah. Yep. Now, what they have in the thumb is rather than having 2 degrees of freedom down at where would normally be the MCJ joint on the fingers, but it's actually called the CMC joint in the thumb, you actually have 3 degrees of freedom there. So that's why they went from 4 to 5 kind of DOF that you would need to have there, and then the actuation for each one of them in the palm, and that's how you get to 24, which is kind of weird. You would think it would be the same number or less. And they're having to do it in rings. So there's like easily 3 rings of 8 actuators on there, where the most important ones seem to be near the top. So if you look at some of the videos, you can sort of figure out which of those actuators is connected to which finger that's movement. You can guess in a little bit of them, but not all of them that are there. The other thing to notice is that as it's going around, those tendons need a little bit of space to breathe, I guess you can say, in their movement. The other thing it might be a little bit hard to see is like, well, wait a minute. I was like, what happened to those big, bulky Popeye forearms that we had?
Yeah.
How are they doing that wrist mechanism? You can't see it very well. It's a little bit behind the wrist. And in that video from Dirty Tesla, there's like a point where the hand moves around a little bit and we get a little bit of a glimpse of where it is. So it's still there. It's hidden behind there. We can see a little bit of the actuation that's going on there and how everything is put together. And they changed the mechanism a little bit. So I have that one video clip showing the Gen 2 versus the Gen 3 wrist design that they've decided to do with an actuation strategy, which as far as I know, has no name to it, except some of the people I've talked to call it a MIMO joint, basically multi in, multi out. This idea, it's a kind of a parallel kinematic. So I made a little simulation showing the two. And I think if you progress to one of those slides, you'll go ahead and see that.
Okay. So we've got Dirty Tesla's recording here.
Yep. And so he's got a nice close up of kind of what's going on. And when we look at it, we can sort of see what's going on down by the tendons. We can see the actuators kind of going up and down and up and down. And as we get in here a little bit, that wrist is going to turn around. It's going to give us a nice little peek on the inside of the palm. But as it comes around, the wrist is going to move, and we're going to get a chance to see what that wrist mechanism looks like, because the actuation of that is happening with mechanisms that are behind right now. But as the wrist starts to roll around, you are going to see where the levers are that are making right there. So on the side, you're going to be able to see those back levers that are moving it up and down, to be able to do it. And that from that, I was able to get a glimpse to see how they've actually modified the Gen 3 versus the Gen 2 on how it works. Now, remember, this is a kind of clever design. It's a parallel kinematic design. That means that if both of those actuators are moving in the same direction, you get this pitching motion of your palm. If they move in opposite directions, you get this yawing motion. And the advantage of that is that your yaw is a motion that's like a little bit, it's a motion you need to have, but it really, to dedicate an entire actuator for it almost seems like overkill. And this way you can kind of split these two actuators just to, if you need to have all the action that way, you've got it. And if you need a little bit of side action on there, you can get that. But in order to do that, your mechanism not only has to be parallel, it has to be out of plane. So I've got another animation that comes up here that shows a comparison between the two. And that animation is in the plane. And we have to remember there's also some out of plane movement. But the most important thing is to sort of understand the idea of what's going on with this. And so if we bring up that animation, we're going to see that we have the actuators that are in the Gen 2 bot, which are very big and bulky. Okay, so right here, we can look at the animation. So we can see the Gen 1 to Gen 2. And you'll notice it's a very simple mechanism. We're down at the bottom of the black actuator. There is what looks like a pin joint. It's actually a spherical joint known as a Heim joint, because of that out of plane nature needs to move around there. So it seems like it's a spherical kind of joint. And up at the top, you can see there's another pin joint up there, but it's actually a spherical joint that would allow sort of the hand mechanism to move back and forth. The main thing about this is that you see that actuator has to move in and out, in and out. You've got to give it space to move back on in there. And, could be a source of things getting pinched in there and needing a bit more access to be able to do it. Now, what they've done in the Gen 3 is they said, well, what we can do is let's kind of turn the mechanism upside down, rather than making it like a 3-bar mechanism, basically make it a 4-bar mechanism, where the actuator is now fixed. It doesn't move. And we add an extra linkage up there, and both of our heim joints are now kind of past the actuator to give the movement that you need, so that the linear actuator is able to always be parallel to itself. You have a kinematic linkage that's connecting it to the pitching motion, or what would be the yawing motion out of plane, to it. And now you'll see it stays way more compact. You're not having it flop in and out, in and out, in and out. And that's what they did. They added that to change it a little bit. So there's some pros and cons to doing that. I think there's mainly pros. The con is like, oh, we had to add one more link. It's like, oh, one more part had to be added in there. And the thing is, but what you get from it is a huge advantage on being able to get it to work. And that was like part of the trick to them being able to make everything so compact in that forearm. Another thing I want to do is just kind of go back to Milan's post about this, and some of the interesting things he says about what they have to do with the forearm, which to me was kind of curious, where he laments about, that they need to do a better job of packaging. It's still like too bulky and too heavy. And I'm like, are you kidding? It's like, I can't believe they got it down to that size already, that, just the hand itself looks very compact. What we saw at We Robot, that looked like a very, very big hand. It looked actually bigger than a human hand. And that was probably the prototype they're working on to test this stuff out. But now they refined it so that the hand is much smaller. And he's talking about some of the things they want to do. They want to reduce the mass. It's too massive. I would not be surprised if it's already the same mass as the original one, because just look at those two wrist actuators. They're pretty big. And now it seems like you can't even find them anymore in that wrist mechanism that they have. The other thing is to remember, not all masses are the same. The original hand, all the actuators are in the hand, and those actuators have mass. And now they've taken that mass and they've shifted it down the forearm. And as you shift it down the forearm, you're moving that mass closer and closer to the center of the body, which is what you want to do. And there's a reason for that. And if anyone wants to sort of, test this out themselves, go ahead and take something that's very, very heavy, take something that's heavy like this, and put it out there in your hand, and then hold your hand out there like that. And you'll notice you get fatigued very, very, very early. But if you take that same mass and then move it to your forearm, you'll notice that it takes a lot longer for you to get fatigued. And just because these are mechanical mechanisms doesn't mean they don't suffer from the same stresses and energy losses that we have. So I've always told my students, if you look at a robot arm, and if it looks like it's uncomfortable and straining from the standpoint of you as a human being, and I'm talking like, big bulky industrial robot arm, it probably really is. There's a good chance that your torque requirements, everything, are very high, because they're having to deal with the same physics that we are. So when you take masses that are like out in your hand right now and you move it back here, you've already gained a lot, even if you've added technically a lot of weight, because in many cases, when it comes to movement, it's not about mass, it's about rotational inertia. And the higher the rotational inertia is, the harder these things have to work. So if they think they can still reduce the mass quite a bit, that means that arm is going to be way more performative than the previous one, not just in dexterity, but the fact that it's, so much thinner. It looks like it could get into any space right now. Nothing's going to get caught on there. And I think the only mystery that was left for me is that when we looked at the arm, that whole gray kind of glove that's on there was very exposed in the lower forearm here, or let me call it the under forearm. Whereas if you look on the top part, it was like, really solid kind of covering on there. And I was trying to figure out why that is. And at first I thought it might have had something to do with the wrist mechanism. Maybe they moved around to there to give it room to move. But as we've seen, that wrist mechanism, you don't need, it's not going to be moving out there. So you can kind of cover it up. I'm thinking they put sort of the fabric or flexible material there because those tendons are still kind of moving around. They need a little bit of room for play in there, and they may be able to do it. But I would think you would want a hard covering there. And the reason you'd want a hard covering is, think about when you're working a lot of stuff, whether it's an assembly task or picking something up, you're dragging that part, this is going to be exposed. So if I'm picking up a box and grabbing a box, I'm going to be rubbing up against that. I don't want something that's kind of soft there. So it's a little bit curious, but remember, this is like a first generation of this that they're putting on there. The other thing that I wonder is that, is the Gen 3 bot basically this with that wrist. I've sort of felt there's going to be other changes going on to the Optimus Bot. Maybe I'm wrong. I mean, maybe that's all that's kind of holding it. They may be happy with a couple little tweaks there. I was expecting that there might be as much of a major overhaul throughout other parts of the body systems to kind of go along with that. It would seem consistent that you would want to do something like that. Trying to think of, where would be some of those places. It could potentially be down in the hip area,
Mm-hmm.
maybe some rethinking of the actuation strategy for the legs, but maybe not, because we saw the recent walking video where they're using the reinforcement learning for the walking. And it seems like they've demonstrated that they do have the reflexes in there. My concern was like, those motors, like they're powerful, they're strong, they can deliver a lot of force, but can they deliver acceleration and velocity? That's what you need. So you need cat-like reflexes a lot of times to keep yourself from falling over and to be able to walk very quickly. And so it may be that now that they're going to the reinforcement learning, that they have that ability now, that they may have more than enough headroom to be able to get up to the walking speeds that they want. So they've never, let's say, expressed any sort of concern. That it's always like, yeah, don't worry about it. We'll get the speed up there. And they're like, yeah, okay, but you're not showing me any progress. So they still have to double the walking speed for it to be useful. And it looks like maybe now they're in the path to be able to do that.
Yeah. Yeah. And then, so that sounds like, I mean, Elon did make an announcement, right? Saying that
Mhm.
they're going to make thousands this year, 2025,
Mhm.
50,000 next year, 50,000 to 100,000 next year, and then 500,000 the following year. So it's, we're as close to design lock as we are. And I think this is it, right? Or maybe one more iteration, like you're saying, maybe.
Yeah. Well, clearly, one more iteration before they scale up, and that was always on the table. I mean, that was since middle of last year. It was said that a couple thousand next year, meaning 2025, for internal use, and then based on the learnings of that, they would make the modifications, and it's the year after that, 2026,
I see.
that they would
Yep.
start scaling up and getting it out to other customers. It doesn't mean to consumers or to the public. It looks like they're already lining up a lot of customers. It's quite possible. A lot of rumors swirling around We Robot. A lot of CEOs that were there that were expressing interest probably in being able to use Optimus when it's ready. So I'm sure they would have the demand for it, and they just want to make sure that the design lock is there. The way Optimus is right now is it may not be suited yet for in the home, but it may be more than suitable for in the factory. And I think we've pointed out this thing again and again and again, is that you're not going to get it at home, not because the bot's not ready for it, but because there are people willing to pay 10 times more than you for that bot. It's
Right.
as simple as that. And these are called business owners. And so until there is a huge supply of these things, it's going to be going into factories at first, which means they can be a little bit rougher on the edges. As a matter of fact, they need to be a little bit rougher on the edges to be able to survive in kind of a factory environment. And when they come into the home environment, at that point, they will have had the maturity that they will be a little bit better to be able to operate around people and small pets and children.
They might do a bot pilot program, letting people like you and me test it out, because the more videos,
you and me, I'm like we're on the list. Yeah, I'm sure. I mean,
for sure we are.
There's a list, and I'll tell you, we're not on it.
Oh, you are, Scott.
Yeah,
but I mean,
there is a list. It begins with an S, I think, somewhere.
Like people who are testing it out, and the more use cases, the more environments, the more videos. That's what's needed now. That's why they're going to make thousands. So, Scott, is this worthwhile that they delayed it? But to actually going for this, we had spoken to other CEOs of other robotic companies, and they said that it's really it could be a fool's errand to try to do this, what they did with the tendons in arms, because it reduces your ability to carry 50 pounds. There's a lot more chances for it to break because they're weak tendons. But they went ahead and went for it.
Yeah, and that's the thing. We will find out, and they will find out. And I'm sure they're aware. I mean, there's a body of research out there looking in tendons. A lot of people that have worked in this, and of course, most of them would say it's difficult. It's a fool's errand. We're not sure you want to go down that way. But then a lot of times, many innovators have been told that you can't do this, and they turn around and they find a way to do it. So if you dog it enough, and again, you just got to remember, everything within the Musk companies is always about first principles. And all you have to do is like go, it's like this works with tendons. Okay, so now there is a difference. This is a living system, and within this living system, we have the ability to repair ourselves. The other thing we have kind of the ability to, and this is what an AI would do, is kind of self-calibrate every morning, because our body is constantly changing, yet somehow we figure out how to do it. And that's what a good AI is going to do. So the question is whether they can make something that's reliable enough to be able to do it. But you that's there. And so that's part of where the dogged determination comes from, is just like, you're telling me it can't be done, yet I see evidence around me in this room. Like everyone that's sitting around this table is evidence that you can do it. So it's not to say that it's not difficult, but it's not impossible. There's no doubt about that.
So Scott, you said it to me earlier, that so much competition out there, right? The Chinese specifically, they're all coming out, lots of demos. How much better is this versus, let's say, here's Optronic that's able to pick and place, right? This is just at the recent CES technology showcase there, and Optronic showed their beautiful robot and is able to pick and place. And we've seen lots of other, how much more TAM, much more business things that it can do, like maybe sew clothes or play piano, but these other competitors won't be able to do. How much more of a business market is that, since Tesla went ahead and went with a 22 degrees of freedom and they invented this new way?
It could be a game changer, because a lot of times you will see a lot of these sort of down market applications is that we have a cheaper bot or something to be able to do the task, because you don't need all the stuff. You don't need the bells and whistles. It's just enough for that. And so clearly you can design bots that will be able to work in that niche. But if someone is able to produce a bot that, not only can it do that, it can do all these other things, and it can do it at the same price, then it's like, wow, wait a minute, which one you get? So what that does is it puts a lot of economic pressure on, if you're going to have something with less capability, the price is going to have to also be a lot less. Otherwise, I'm going to go with the other guys. The only reason that maybe I won't go with the other guys is that they're just not available. Because they get so many other people. So sometimes you have no choice. You go with what you want. I mean, a lot of times, we've walked into a cell phone store and wanted to buy a certain cell phone because we urgently need one, but nope, they don't have that one. So you just got to buy the one that they happen to have. So you could be seeing things like that, but it at some point, everyone else will have to up their game to be able to do something similar to that. And, a lot of it is also going to come down from the training. How good is everyone's AI going to be? Is that you can have as good a hand as you want, but if it actually can't do a task very easily, that's also going to be a problem. So all these pieces have to come together. You have to have a good brain, you have to have really good mechanics, and you have to have a pretty good hand, because at the end of the day, the business end of the robot is the hand. Everything else is just about getting the hand to where it needs to be. So walking and backflips are all very nice, but it really doesn't matter. All I need those legs for is to be able to position my hand to where it needs to be to do its work. And so sometimes you need to have a certain amount of dexterity legs to be able to do it, because you have these challenging configurations, but everything is there. So you can have this beautiful bot that does everything, but if its hands are absolutely non-functional, then it's a curiosity more than anything else, than something that's actually going to be useful.
Okay. So the hand is important, but like you said, the brain as well. The good news about Optronic is they have a partnership with Google DeepMind.
Yes.
And that's who their investors are. So that sounds like it's going to be a big deal. And then of course, Tesla went ahead and did the 22 degrees of freedom. Thank you so much, Scott. This is a deep dive on why they did it, what they're working on. It looks like that it's functioning really well. And you showed how the tendons are working now. Much more human-like. So we'll see where this goes. But yeah, I'm looking forward to 50,000 Optimus next year.
Yeah, I think that's possible. If the design is good, I don't see any reason why they couldn't scale to that.
Wonderful. Thank you so much, Scott. Follow him on his X account at Going Ballistic 5. Thanks, everybody. Bye-bye. I've created a website that is the most comprehensive resource for the Tesla investor. Please check it out. Simply go to my website at herbertong.com.